Hello everyone and welcome. Today, we are diving into the world of operating systems to explore a scheduling algorithm known as priority scheduling. This method is all about giving preferential treatment to certain processes over others. In this presentation, we will explore priority-based algorithms and priority inversion in operating systems. So, what exactly is priority scheduling? First, each process is assigned a priority value. Think of it as a ranking system where some processes are more important than others. The CPU or central processing unit, which is the brain of your computer, is allocated to the process with the highest priority. This means the most important task gets the CPU's attention first. Priority scheduling can be either preemptive or non-preemptive. We'll delve into what these terms mean shortly. Finally, priorities can be static, meaning fixed, or dynamic, which means they can change over time based on certain conditions. The diagram here shows a priority queue, with process A having the highest priority, followed by process B and process C. The CPU will execute these processes based on their priority order. Now let's explore the two main types of priority scheduling: preemptive and non-preemptive. First, preemptive priority scheduling means that a higher priority process can interrupt a running process. If a critical task comes along, it can immediately take over the CPU, ensuring critical processes get immediate attention. Preemptive scheduling is often used in real-time systems where immediate response is crucial. The code snippet here illustrates this concept, where a new process with higher priority can preempt the current process. Second, non-preemptive priority scheduling works differently. Once a process starts running, it completes its CPU burst, meaning it finishes its task before another process can take over. New processes wait regardless of their priority. Non-preemptive scheduling is simpler to implement. The code here demonstrates that the scheduler selects the highest priority process from the ready queue, but it doesn't interrupt the current process until it's finished. Let's walk through an example to illustrate how priority scheduling works. Consider this table of processes, where each process has an arrival time, burst time, and priority. Process 1 arrives at time 0, needs 5 units of burst time, and has a priority of 2. Process 2 arrives at time 1, needs 3 units of burst time, and has the highest priority of 1. Process 3 arrives at time 2, needs 4 units of burst time, and has a priority of 4. Process 4 arrives at time 3, needs 2 units of burst time, and has a priority of 3. In preemptive scheduling, the Gantt chart shows the execution timeline. Process 1 starts but is preempted by Process 2, which has higher priority. Process 1 resumes, then Process 4 executes, followed by Process 3. The average waiting time for these processes is 4.75 units, and the average turnaround time is 8.25 units. While priority scheduling is effective, it presents certain challenges, notably starvation. Starvation occurs when low-priority processes may never get to execute if higher-priority processes keep arriving. This is a critical system issue that can lead to resource underutilization and can cause system instability and process timeouts. Fortunately, there are solutions. Aging involves gradually increasing the priority of waiting processes. Priority boosting periodically boosts the priority of all waiting processes, giving them a chance to run. Time slicing combines priority scheduling with round-robin scheduling for processes of the same priority. The diagram illustrates starvation, where high-priority processes continuously arrive, preventing the low-priority process, Process 5, from ever getting CPU time. Another significant challenge in priority scheduling is priority inversion. Priority inversion occurs when a higher priority process is indirectly preempted by a lower priority process. This typically happens when a high priority process needs a resource that is currently held by a low priority process. The classic priority inversion scenario is illustrated here. A low priority process acquires a resource, then a high priority process becomes blocked waiting for that resource. Meanwhile, a medium priority process executes, further delaying the high priority process. This situation highlights the priority inversion problem, where the high priority process is effectively blocked by a medium priority process due to the low priority process holding the needed resource. To address priority inversion, two primary solutions exist: Priority Inheritance Protocol and Priority Ceiling Protocol. The Priority Inheritance Protocol dictates that when a high priority process is blocked by a lower priority process, the lower priority process temporarily inherits the priority of the blocked process. This ensures that the low priority process can complete its task and release the resource, allowing the high priority process to proceed. The code snippet here shows how the low priority process temporarily boosts its priority to match the high priority process. Alternatively, the priority ceiling protocol assigns each resource a priority ceiling equal to the highest priority of any process that may request it. When a process acquires a resource, its priority is temporarily raised to the ceiling priority. This prevents medium priority processes from interrupting the low priority process holding the resource. The code illustrates how a process acquiring a resource temporarily elevates its priority to the resource's ceiling priority. Let's recap the key takeaways from our discussion on priority scheduling. First, priority scheduling assigns CPU time based on process priority. Second, it can be preemptive or non-preemptive. Third, starvation is a major challenge that requires aging or boosting techniques. Fourth, priority inversion occurs when high-priority processes are indirectly blocked. Fifth, priority inheritance and ceiling protocols solve priority inversion. Sixth, priority scheduling is often combined with other scheduling algorithms. In the real world, priority scheduling has numerous applications. The Mars Pathfinder mission famously encountered a priority inversion bug that caused system resets, which was later fixed with priority inheritance. It is also used in real-time systems where timing constraints are critical, and in mobile operating systems where UI processes get higher priority to ensure responsive interfaces. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.